Math 2414, Surface Area of Revolution, Video 5. Surface Area, Example 3. If you just got finished watching the previous video, you may look at this problem and go, it's exactly the same as before. And you would be correct. To find the lateral surface area of the solid obtained by revolving the graph of y equals x squared from the point 1, 1 to the point 2, 4 around the y-axis. But the reason I set up the exact same problem is following through on a thought that I had at the end of the previous video. That this curve from 1, 1 to 2, 4, which is being rotated around the y-axis, can be viewed as a function of y because it passes the horizontal line test. In other words, I can think of this as x equals g of y, so some function of y. But if I'm going to do that, then I should take the equation and solve it for x, so it says x equals a function of y, which is easy to do. Square root both sides, and you get x equals the square root of y. Same curve, same solid, should be the same surface area. And since this is a function of y, let's go ahead and explicitly call it g of y. And by the way, the name g is totally inconsequential. I could have called it f of y, g of y, h of y, any function of y. I just try to be consistent. If it's a function of x, my default is f of x. If it's a function of y, my default is g of y. All right, so if we're going to think of this as a function of y, then our surface area is going to be the integral. Let's give you the same thing as it was before. We're rotating it around the y-axis. The axis of rotation dictates what the radius is. In this case, it's the opposite. It's always the opposite variable, so it's still going to be 2 pi x. But because I have a function of y, when I unpackage the ds, I'm going to unpackage it as this: the square root of 1 plus the square of the derivative of g of y dy. And so this is a dy integral. And so our limits of integration will be from the lower y to the upper y, 1 to 4. But that's not the biggest change. The biggest change is I'm doing a dy integral and there's an x. And we're not in multivariable calculus yet. That's the next class. So we're not going to have an x inside when we're doing a dy integral. We need to replace the x with something that is equal that contains a y. Oh, x is equal to the square root of y. Times the square root of 1 plus. And let's go ahead and figure out what the square of the derivative is. So let's go over here to the side and figure that out. G of y is equal to the square root of y, but we're about to do calculus, so no radicals, please. Y to the 1/2. The derivative of that is 1/2 y to the negative 1/2. Let's go ahead and rewrite that as a single fraction with a 1 on top, 2 on the bottom. The y to the negative 1/2 would go downstairs, become y to the positive 1/2, but then become a square root again because I'm going to pause the calculus and do some more algebra. I have to square this, which is easy now because I can just square all of it. 1 squared is 1, 2 squared is 4, and the square root of y squared is y. So that's what the square of the derivative is. Now that we have the integral set up, let's just try to do it. And, you can have all the techniques in the world, but you may run across a new situation and you're not sure where to go, this being one of them. It's not really that difficult if you make the correct first move, it just may not be obvious what it is. So I want you to think for a second. Before we do any calculus, is there any algebra that we can do to maybe change the integrand to make it easier to work with? I give you a hint. It has to do with the fact that there are 2 square roots being multiplied. Well, as long as at least one of these radicands is positive, and they both are over this interval, you can multiply 2 square roots together by multiplying their radicands. In other words, you can, under most circumstances, multiply the 2 square roots together into a single square root. The only time you can't do that is when both radicands are negative. So for example, if you have the square root of negative 4 times the square root of negative 9, that is not equal to the square root of 36. Don't believe me? This is 2i, this is 3i. 2i times 3i is 6i squared, which is negative 6. but this is positive 6. But, excuse me, that's the, that's the only situation where you can't multiply two square roots together, is when both radicands are negative. All right, but in this case they're not, so we can. And that invokes the distributive property. Integral from 1 to 4 of 2 pi square root of. If we distribute the y to the 1, we just get y. But if we distribute the y to the 1 over 4y, the y's would cancel, leaving y plus 1/4. And now we have a pretty easy integral. I'm going to let the 2 pi just sit there. It's not doing anything. But I'm going to rewrite the y plus 1/4, the square root of y plus 1/4 as y plus 1/4 to the 1/2 power. Because once again, we're about to do calculus, and we don't do calculus to radicals. We do calculus to powers. Technically, you would do a substitution here, but I want to remind you that if you're going to do a substitution like u equals y plus 1/4, but du is just equal to dy, there's really no need to do the substitution because you don't have to worry about balancing out the du package. You can just straight up integrate using the rule that you would use. And that rule would be, there's the 2 pi, add 1 to the power, so we get 3/2, multiply times the reciprocal, which is 2/3, and this is being evaluated from 1 to 4. Well, this doesn't look like it's going to be too terribly bad. The 2 pi times 2/3 up front is going to be 4 pi over 3, and now we just have to substitute the upper and lower limits and subtract them. I'm not going to dilly-dally with the addition. Adding a whole number and a fraction shouldn't be an issue. 4 plus 1/4 is 17/4, so we have 17/4 to the 3/2 power minus 1 plus 1/4 is 5/4, so we have 5/4 to the 3/2 power. And at that point, you might be thinking, we're done, but that ain't the answer we got before. Well, no, and yes, it is. It may not seem obvious, but let's take that expression over here and let's see if we can simplify it. Because believe it or not, the best calculus students sometimes have really shoddy arithmetic skills, especially when it comes to radicals and fractional powers. So let's take this guy real quick and see if we can massage it into the answer that we got before. Now, if you may recall the answer that we got before from the previous video, and if you didn't watch the previous video, you should probably go back and watch it. I should have said that at the beginning. But in the previous video, I believe the answer we got was pi over 6 times 17 squared root of 17 minus 5 squared root of 5. And you might see remnants of that in the answer that we currently have. There's a 17, there's a 5, there's a pi, but the fraction is wrong in front, and we got some fractions on the inside, and I miscopied. This is not a 2, this is a 4. So what would motivate you on how to clean this up? Well, you have to know that a 3/2 power means cube and square root. Third power, square root. And although I can't square root 17 or 5, I can square root the 4. The fact that I can square root the 4 means that I can raise it to the 3/2 power cleanly, which is motivation to distribute the power across each fraction. 4 pi over 3, 17 to the 3/2 over 4 to the 3/2 minus 5 to the 3/2 over 4 to the 3/2 is looking a little bit better because these two guys will become these two guys. But as far as the 4 to the 3/2, the half means square root, and the 3 means third power. Square root of 4 is 2, 2 to the third power is 8. Both of these have a denominator of 8. And let's go ahead and turn the 17 to the 3/2 into 17 squared root of 7 over 8. And the 5 to the 3/2 into 5 squared root of 5 over 8. Getting there, but to get that answer, we would have to factor out the 1/8. If we factor out the 1/8, that would leave inside the parentheses 17 squared root of 17 minus 5 squared root of 5. So that part's there. And then over here, the 4 and the 8 will reduce by 2. Excuse me, the 4 and 8 will reduce by 4. 4 disappears, 8 reduces to 2. And in the bottom we have 3 times 2, which is 6, which is living underneath a pi, times 17 squared to 7 minus 5 squared to 5. So again, I don't think this one was that terrible. There was a small algebra move right before we integrated where we combined the square roots and distributed, but it did turn into something that was integrable. And we did end up getting the same answer as before, which we should have because it was the same solid, so it should have the same surface area. The point of this video was to show you that there is more than one way to do some of these problems, depending upon if you view the curve that you're rotating around an axis as a function of x because it passes the vertical line test, or a function of y because it passes the horizontal line test. You won't always be able to do a problem 2 different ways, but if you can, you should get the same answer each time.